I would like really to briefly introduce him to allow him more time. So he's a professor at the University of Suam, and his focus is really on fisheries ecology, especially recruitment variability, focusing on early life histories of fish related to oceanic and climate change. So Dr. Kim Suam has represented Korea in several international organizations, among them PCs, Globek, Kamlar, SCORE, and he serves now as a co-chairman of the joint PCs IC section on climate change effects on marine ecosystems. Please join me, welcome Dr. Kim Suam. Thank you.
Thank you, dear. It works?
Yeah, it works.
And it is my great honor and pleasure to be here because the UBC Fisheries Center is very famous, world famous institute. So as a fishery biologist, fishery scientist, it's really one of my dreams to have a talk here. And today's talk is about a kind of a comparison study, comparison of ecological characteristics of fish communication, fish communities, and oceanographic features in coastal areas of Western and Eastern Pacific. So actually, this area, you don't have a laser point.
Sorry.
These two areas, the study I choose, but before I talk on major topic today, I try to introduce some fishery status in Western Pacific areas and try to connect that to my topic later. Maybe this is a famous figure. Most of you are already familiar with it. The overview of world fisheries in 2010, the captured fisheries record around 90 million metric tons. And aquaculture is rapidly increasing. Right now, it reached about 70 million tons in aquaculture production. So aquaculture production is increasing, and captured fisheries is kind of stable for last 2 decades. If you see fisheries statistics collected by FAO, and it indicates the northwestern Pacific area, the area called Area 61, showed 20 million metric tons per year. At that time, the world fisheries total is about 80 million. So at least 25% of fish production was produced from the northwestern Pacific area. If we include some Southeast Asian fishery production, Area 71, then we can add another 11 million metric tons. So total around 30 million metric tons of fish production was from west side of the Pacific Ocean. Thank you very much. The production of Western Pacific indicates around 30 to 35 million metric tons every year since the 1990s. That is about between 30 to 40% of world catch. So if we compare the production in other areas, the production in Western Pacific is much higher than any other places. So that's why they call the East Asian area is kind of a food basket of the world. In 2006, the East Asian production account for 36% of the captured fisheries, and also 80% of aquaculture production from this area. So this area really produces lots of fisheries production. And also in this area, more than 3 billion people reside here, and they produce lots of fish production here from aquaculture and capture fisheries. And consumption is very high, and world trade, they contribute a lot of fishery product in international trade. So this area, especially in fisheries field, really important in the world. Okay, let's see the original topic. In the North Pacific Ocean, there are two big giant systems. In the low latitude, there is a clockwise system with warm water. In the high latitude, there's another small giant system here, and usually that is cold. But if we compare those two areas, east and west, there are some differences. In the coastal area of the Western Pacific, relatively broad continental shelf form here, and also two water masses, two currents merged here of the Japanese islands, and they move toward the east. The offshore Canada here, near the Vancouver Island, they divert two directions, the Alaska or California. So ecosystem, the two ecosystems are a little bit different characteristics. And warm water here, and the water temperature is a little bit higher than this area, and the currents merge here but divert here, and some a little bit low latitude, a little bit higher latitude. Again, this figure that produced in area 61 produced about 20 million metric tons, but the northeastern area they produce 3 million metric tons per year. So I will have a briefly analyze this area, fish composition of this area. And area 61, the northwestern Pacific area. If I divide the fish group like this, the vertebrate pelagic fish and demersal fish. For the invertebrate, demersal kind species or demersal group and pelagic group. Then, as you can see, the pelagic fish and the demersal fish maybe occupies half and half since the 1970s or 80s. And this fish production is much higher than invertebrate fish production in area 61. But basically, the composition of two groups are not much difference in terms of amount. Area 67, the northeastern Pacific Ocean, is a little bit different. The demersal fish species occupies a lot compared to the pelagic fish species. So here in the northeastern Pacific area, demersal fish species the production of demersal fish species is more than 2 million metric tons, but for pelagic fish, less than 1 million. And also, in vertebrate production, the demersal group is a little bit, there is some production from demersal groups, but for pelagic invertebrate, it's almost nothing. But as you remember, the northwestern area, invertebrate pelagic, that's mostly squid, common squid, that occupies some amount. So the number of commercial species in area 61 and 67 indicates many commercial species in the area 61 compared to northeastern Pacific area. So in terms of the number of fish species commercially used is much higher in area 61 compared to 67. But if you look at the proportion of demersal fish, pelagic fish, and invertebrate demersal, then it's very strange. The proportion very similar. The demersal species occupies a number. I'm talking about that number, 42%, around same, and pelagic fish species around 28%, and invertebrate demerger occupied 21%. So my study will focus on the boundary area, western boundary area in eastern and western Pacific area for the comparison purpose. And also, the purpose is to identify the changes in space composition in two ecosystems during the last 2 decades, how they changed. And finally, try to provide the basis in fisheries management under changing environment, especially climate change. The study area is this. In the Western Pacific, we choose Japan and Korea. And in the Eastern Pacific area, we choose the area from British Columbia and state of Washington and state of Oregon. So in the Western Pacific, as I said, the two currents merged from here toward the east. And in the Eastern Pacific, current came from the west and diverted here. The data I used for physics environments is sea surface temperature information from the soda, and also this data I regarded the temperature at 5 meters as a SST. So I used the only winter SST data. And climate index, I choose 4. PDO, Pacific Decadal Oscillation Index, and AO, Arctic Oscillation, and SOI for El Nino, RP, Louisiana Low Pressure Index, I choose. For fishery information, basically I used for FAO information for Korean fisheries and Japanese fisheries. And for Eastern Pacific area, I choose some Canada fisheries statistics for BC area, and also I selected some information from Oregon and Washington fisheries statistics. And also for reference for fish habitat, I use the fish base. And for statistical method, I use some QSUM and cross-correlation functional analysis. The climate indices indicates maybe each climate index shows different pattern, but basically tendency is very similar. In RP and PDO, or AOI, or SOI, these 3 things are similar, but basically they have some kind of reflection point in the middle of 1970s. As you remember, there's big changes in climate in the middle of 1970s. So we call it climate regime shift. So all climate indices show some big changes in 1970s, and some minor changes in the late 1980s and also late 1990s. I compare the winter SST in Eastern and Western Pacific areas. In the Western Pacific area, since 1970s to current, around early 21st centuries, that shows some kind of increasing trend here. And the increasing trend is a little bit conspicuous, clear compared to the Eastern Pacific area in the Western Pacific. And also the Western Pacific area temperature is relatively higher than that of Eastern Pacific area. If I choose 2 periods from each ecosystem, I choose early 1980s and early 20s. Then in the Western Pacific area, a cool phase appeared in the early 1980s, and 2 decades later, in the early 21st centuries, it became warm. But at the same time, when this ecosystem is cool, the Eastern Pacific area, that is warm compared to the 2 decades later. So there is some kind of alternative patterns. For the comparison reason, I just choose 2 periods. 1984, that's the early 1980s, and also I choose 2000 February, that's early 21st centuries. As I said, this Western Pacific area, at the time, the temperature is relatively cooler. But 2 decades later, it showed some warm temperature propagate this area a little bit more. So this area became milder and hot, warm environments. But in the Eastern Pacific area, that was warmer, but 20 years later, the cooling pattern was more stronger than 2 decades years ago. Just if I see the difference between 2 decades for winter SST, then this figure indicates some warming was serious. Warming effect is more serious here, but in the Eastern Pacific area, even some cooling we can find. But from this slide, what I would like to say is, even there is a global warming, but in Pacific Basin, the warming is not always happen for one big area. So warming or changing climate is depending on a local basis or regional basis. I try to combine this oceanic environment with the fisheries catch information. So in the Western Pacific area, Northwestern Pacific area, the temperature, seawater temperature in 1980s was cool at the time. But after then, from 1990s, this water became warm. I added a fish catch here, the pelagic fish, demersal fish, invertebrate. Then pelagic fish and demersal. The demersal also tend to decrease, but pelagic fish species much fast decrease. So proportion, relative proportion indicates in 1980s, higher proportion of pelagic species here in 1980s, but it was decreased a little bit since 1990s. But still, pelagic species is much higher than demersal species. So most representative species in pelagic fish species is Japanese sardine and chum mackerels. And for demersal fish, mostly walleye polla, and for invertebrate, clams and squids. In the Eastern Pacific area, the pelagic species kind of shows the decreasing tendency a little bit. But in absolute amount, demersal fish species is much higher than pelagic fish. And demersal fish increased through middle of 1980s, and it was quite stable in 1990s, but showed a decreasing tendency in the 21st century. But a relative proportion indicates the hakes, especially, and the hakes and rockfish occupies a lot in British Columbia and Washington, Oregon coastal area. And some sardine and herrings, relatively small portion. And if we look at the catch ratio from the Western Pacific area, there's I can choose 20 representative species from each ecosystems. And Japanese pilchard in 1980s, the left side is 1980s, early 1980s, right side is early 20th century, 21st centuries. If you look at the top ranks in early 1980s, then Japanese pilchard, that's a sardine, occupies a lot. As a single, this single species occupies 36% of total production there. And the second largest one is the walleye pollock, and some chum mackerel and anchovy follow. But 20 years later, the Japanese pilchard disappeared. Rather, Japanese anchovy occupies the highest rank, and chum mackerel followed, and flying squid third. But in 21st centuries, even the rank 1 Japanese anchovy, they only occupy the 11%. And chum mackerel, the second largest, that's about 9%. So some species share as a dominant species group. So if you look at this table with a figure, then in early 1980s, at the time, the water is full, and the major species is Japanese pilchard, but that it disappeared 2 decades later, and some minor species become a dominant. And in this period, some species, 4 or 5 species, had showed a similar proportion catch. In the Eastern Pacific area, in 1980s, there's rockfish occupies 13%, and herring, egg, and salmon, pink salmon, occupies another 10%. This period, this area is a little bit warmer than 2 decades later. And early 21st century, hake occupied 36%, and other species occupied the rest of them. So if we see that table with figure, then in early 1980s, the 4 or 5 species took around 10% each, but 2 decades later, the dominant species become minor, and minor species become dominant. And especially the hake species occupy more than 30%. So if I choose some dominant species, the sardine was abundant in Western Pacific area in 1980s, but it became minor. But in the Eastern Pacific, hake was not much abundant there, but it became abundant since 1990s. And other species like pollock or some mackerel, they show the kind of decreasing trend or ultimately stable. But I'm showing what is some dominant species like sardine and hake. They showed dramatic changes in each ecosystems. And also I tried to make a correlation with the climate indices with some fish catch for some species. I selected some statistically significant examples from my analysis. For example, pilchard and PDOI has a significant correlation at time scale of 0. But some species, like pollock has a significant correlation with the PDOI with a time interval of 2 or 3 years. So still, I have no any concrete idea what processes affect on what climate effect, what kind of processes in the wild environment. So climate through the oceanic processes, the ecosystem can be changed, or they may affect on some physiology of fish species, but still the mechanism is not very clear. But statistical analysis indicates that there are some kind of a relationship between environment and fish biology. So I can find some kind of significant correlation in Eastern and Western Pacific area, but still in the future, maybe it's better to get into deep for this analysis. And the number of important species in the Western and the Eastern Pacific area indicates even there are big differences in fish catch. In the Western Pacific area, the southern boundary of the subarctic ecosystem, they produce in 1980s more than 8 million metric tons. But in the Eastern Pacific area, the production is much less. But even there is some difference in catch amount, but this kind of analysis indicates the species, number of species in the Western and the Eastern is not much different. So in the Western Pacific area, the commercial species, we found 135, but Eastern area, around 100. The composition of this, the demerger occupies 33%, one-third, and the pelagic is a little bit higher than demerger. The rest of them is invertebrate. In the Eastern Pacific area, the demerger is a little bit higher than pelagic fish species, and some invertebrate species occupy this amount. I look at I try to compare the biological characteristics in each ecosystem. So Western Pacific area, there are many fish species, but most fish species have a very short lifespan. Here, Japanese pilchard, maybe 25 years, walleye polar, 15 years. This is based on fish base, but actually, the local biologists that are there do not think this fish can live 25 years, and walleye polar, 15 years? No, I don't think so. But actually, anyhow, the longevity of this fish species is much less than that of Eastern Pacific area. Here, Eastern Pacific area, many fish species live very long period. Some fish live longer than 200 years, and also the rockfish species mostly live more than 80 years or 70 years, something like that. So longevity here in the Eastern Pacific coastal area has a long lifespan, and also I look at the habitat, depths of residence, and in the Western Pacific area, the pelagic fish species are relatively bigger than the demerger fish species, but the Eastern Pacific area, maybe the demerger species is bigger. So climate. Right now, the climate change is a big issue in any field of society. Even in fisheries and oceanography, same. If there's a changing climate, maybe in the ocean, some changes in environment, like seawater temperature increase and sea level increase, and some waters became acidified and oxygen reserve was decreased. Then that influences the ecosystems. So ecosystem can be reconstructed, and also fishery resources can be changing. So in such rapidly changing environment, we have to consider about the global warming and changing environment, and the sea level rise, and storm disaster, and other unknown factors. So I this is a famous figure about the temperature changes in prediction of global temperature changes according to IPCC AR4. It indicates very higher temperature we can see at the end of this century. And the sea level same. So this rectangle is the current period. We are around here. So in our next generation, our daughters and sons, they will experience totally different environment. Eastern Pacific area, the increasing temperature warming rate of Eastern Pacific area is kind of 0.04 per year. That is nearly similar to the world ocean, world average. But in the Western Pacific area, the warming speed is 1.5 faster, so 0.46 degrees Celsius per year. This is a kind of air temperature increase. In the ocean, as you see, the Western Pacific area, like Northwestern Pacific area, that area, the warming rate of that area is the kind of world fastest, with some northeastern Atlantic area and some other areas. So the area has showed a very high warming rate, and the fish biology or fish catch is a response to change of environment. For example, the chum mackerel catch in the Western Pacific area showed high catch during the warm period and low catch during cool period. And William here made a scientific paper about the climate change impact on fish distribution, and he concluded the fish distribution moved toward forward movement of 40 to 45 kilometers per decade. And in Korean waters, we examined the with the mackerel, and that showed similar conclusion. When the temperature is cool in 1980s, mostly southern distribution, but it distributed in the northward in the warming period. Also, common squid, that is one of the most important fisheries in Korea and Japan, and their spawning ground during cool regime distributed in the southern area compared to warm regime. So as the temperature, the climate changed to warm, their spawning location could be moved to forward. And also, the common squid spawning time is delayed. In 1970s and 80s,